So today's topic is entanglement detection, but since I want to present some concrete examples, we first have to go through some specifics about qubits, because there are some kind of formalisms of block sphere and all of these things that we use for qubits that are usually very handy if you want to present concrete examples. Did you already do this, the block sphere and how it works and everything? Okay, so I'll just go very fast just to set the notation and make sure we are all on the same page. Okay. Qubits and block sphere. So if we are dealing with qubits, our Hilbert space H has dimension 2, because qubit is as a shortcut of quantum bit, and the bit is a two-level system, so we want a two-level system, a quantum one, so Hilbert space with dimension 2. And in this case, you can realize that if you have a Hermitian matrix, it's going to roughly look like this. You're going to have A and B here, Z and Z bar here, where A, B are real numbers and Z is a complex number. Why this? Well, because the Hermitian conjugate transpose must be equal to it, so on the diagonal you must have real numbers, and here these ones must be a complex conjugate of each other. Okay, but this means that this matrix, so let's call it the matrix A, that A can be written in the following way, that I can write it as 1/2 of R0 times identity plus Rx sigma x plus Ry sigma y plus Rz sigma z, where these sigmas are nothing else but Pauli matrices, so you probably know these already from standard quantum theory. And what we did here is that you can see that A and B are going to be obtained from R0 and Rx. So A is R0 plus Rx, B is R0, A is going to be R0 plus Rz, because this one, not that one. And B is going to be R0 minus Rz, and clearly if I have A and B, I can express them as this plus that and this minus that. And here what we get is that the real part of Z is going to be Rx, the imaginary part of Z is going to be Ry, and then we get exactly this form of the matrix. Now, we are not interested in arbitrary matrices, we are interested in density matrices. And density matrices have two notable properties. The first one is that they have trace equal to 1, and the second one is that they are positive semi-definite. So if we want to have rho such that rho is positive semi-definite and trace of rho is equal to 1, then the question is, what conditions do we get on these coefficients? So the first one is rather obvious. This we get from trace, because if we would trace this, then we would get 2 here and 0, 0, 0. But there's 2 and there's 1/2, so the trace would be just this R0. So from this we just get R0 equal to 1 for every density matrix. About the positive semi-definiteness, so this part, here we are going to use a small lemma. And this small lemma says that if you have a positive semi-definite matrix, then the trace of the matrix is positive and the determinant of the matrix is positive. And if the dimension of your Hilbert space is 2, then this is actually equivalent. Okay, so in general, if I have a positive semi-definite matrix, the trace and determinant must be positive. If I have dimension equal to 2, then these are actually sufficient conditions. For example, for 3x3 matrices, you can find matrices where this is already not sufficient. how to prove this? So do you remember what it means for a matrix to be positive semi-definite? Yeah?
Yeah, which of the 4 definitions do you want?
I want the one which is something about eigenvalues.
Okay, and then it's all eigenvalues are positive.
So lambda I, where these are the eigenvalues of A. Now, trace of A is, since I can perform the trace in the eigenbasis or the basis of eigenvectors of A, is nothing else than sum of eigenvalues, and sum of positive numbers is going to be positive. And you might know from linear algebra that determinant is nothing else than just the product of eigenvalues, which is going to be again positive since we're multiplying positive numbers. So this proves this implication. How do we do the other one? So for 2x2 matrices, yeah?
You can express the eigenvalues as functions of gathered traits in 2 dimensions.
Yes, but that's like too hard for me to do. I don't want to do that. That's too much thinking. So try to think intuitively. We have 2 conditions here. Why should 2 conditions be enough?
Both eigenvalues have the same sign, like because the determinant is greater than 0, and then the sum of those 2 is positive, so they have to be positive.
Yes, that's the proof. So let me continue here. So if we have dim h equal to 2, then there's just 2 eigenvalues, lambda 1 and lambda 2. And this is the intuition for why this is enough, because you have 2 conditions for 2 eigenvalues. This is also why it fails for 3x3 matrices, because you have 3 eigenvalues but 2 conditions. So clearly you cannot capture everything. But if I have 2 conditions, 2 eigenvalues, then the determinant of A is just lambda 1 times lambda 2. Must be positive, so they have the same sign, which we can then mathematically say that sine of lambda 1 is equal to sine of lambda 2. But then trace of A is this, and since this is positive, the sign must be plus. Very good. And now the beautiful thing happens, because now we can say that, okay, what we wanted to do is that look at this condition that rho is positive semi-definite, and all we have to check is that the trace and determinant are positive. The trace is obviously positive because we set it to 1 by hand, so the determinant is the only thing that we need to look at. So now I can test basic linear algebra. What's the determinant of 2x2 matrix?
Diagonals minus the diagonals.
Yes, exactly. And this is the only case that you have to remember by heart, because that 3x3 is already too complicated. So what do we get? We get here 1 plus rsat, 1 minus rsat, rx minus I, ry, rx plus I, ry, which will imply that the determinant of rho will be equal to that minus that, so we get 1/4, which we should not forget, but it's not going to play any role at all. And here we get 1 minus rz squared minus rx squared minus ry squared, and this has to be positive. And now this is the magic thing, because this is nothing else than just saying that the Euclidean norm of this vector, because these are 3 numbers that I can interpret as a vector, is less than 1. And now we can draw this standard picture that people usually draw, is that we are going to have a ball, we call it the block sphere. It's going to be the center. We have the x, y, and z direction. And usually you can put here the sigma z projectors. Here in the x direction, you can put the sigma y projectors. And here in the y direction, there would be the sigma y projectors, but we don't have a standard formulas for those, where, of course, this plus is just the superposition of 0 and 1. And this minus is the other sign of the superposition. Yes. So everybody seen this before, or only half, or? Okay. Very good. So we can now jump to entanglement detection. And these are essentially two problems for the price of one, because entanglement detection can be done at two levels. You can do this in theory, or you can see this as a theoretical problem, or you can see this as an experimental problem. The theoretical problem is that we know what the density matrix is. So we are given some kind of density matrix, and our goal is to ask whether is rho separable. Now, this is already a hard problem. And in principle, computationally, it's NP hard. Which NP hard, do you know what NP hard is? So it's usually computer scientists say it's NP hard, it just means like it's very hard and don't really try to solve it. I mean, but in practice, we just get many criteria. And if you want to solve this problem, you just have to try what works. So in practice, there's no like unique way to solve this. It's a little bit of an alchemy. You have to look at your state, try different criteria, maybe do something numerically, and see what you get. Sometimes you get nice results, sometimes you get nothing. The experimental problem is essentially the same, but we now want to do this in experiment. So what we want to do here is to design experiment that certifies rho AB is not separable. Now, this is a little bit harder problem than the theoretical problem, because in the theoretical problem we have many criteria, but not all of those criteria directly transform into experimental designs, you know? So some of them, for example, entanglement witnesses, if you have an entanglement witness detecting your state, you will see that it somehow makes sense how this would be measured. Some of the other criteria are like, well, okay, I can prove the state is entangled in theory, but now I have to figure out how to do it in experiment. So there's a little gap between these two problems. Also, if you want to do this in practice, and even if you design something, the experimentalists usually come and tell you that, wait, but we cannot measure this, and this will be this noisy, and this will be that. So it's like even more headache if you're actually trying to do this. But then also the results are usually more interesting. But for this reason, we'll be mainly looking at this part. And if you want to do this in an experiment, you basically will have to think a little bit harder about how to get a witness or how to get something that's experimentally measurable. And if you want to actually do that, talk to the experimentalist first to see what they can measure. Because usually even if you say that, oh, measure this, then they can tell you like, no. But all of these theoretical problems, they have some kind of standard form. And this is what I mentioned in the last lecture. This is the logic that's very important to understand. And the standard form usually is as follows. We are going to have a state, row AB, which is going to be a density matrix on two Hilbert spaces. And we are going to assume row AB is separable. Then we are going to derive that some either equation or inequality holds. And then, given sigma AB, which is the state that we want to test, we check whether the equation or inequality holds. If not, then sigma AB is not separable. So here's the important part. We have some equation or inequality, which is going to be the criteria. And we're going to prove that it's true for all separable states. And then, so this is something like a theoretical preparation. This you can find in the lists of entanglement criteria or on Wikipedia or in a paper or something like that. And then given a state that we actually want to test, we are going to check whether this equation or inequality holds. And the important part is that if not, then it's not separable. Because we know that if it would be separable, it would have to hold. So if it does not hold, it cannot be separable. But if the equation or inequality does hold, this doesn't tell you anything. You know, there will be no one-size-fits-all solution except for the most simple cases. So if it holds, you just have to try something else. And this is the important thing to remember, that this is why it's hard. This is why we have to try many criteria and see what works. And by working means not holding, okay? The logic will be just essentially now using several times on repeat. So is this clear? So the simplest of these are entanglement witnesses. And witnesses, like in the court cases when somebody witnesses a crime. So these witnesses are not going to witness a crime, but an entanglement. And these are going to be operators. So there are just linear operators on A tensor B, such that we are going to have two properties. The first one is that if we trace this against any, this should be row, any product of density matrices, this will be positive for all row A in density on HA and for all sigma B in densities on HB. And moreover, we add other condition is that trace W row AB is strictly negative for some, this is important for just some row AB in this one. Now, since there's very few letters in the alphabet, I would like to point out that this row A is different operator than this row AB. They belong to different sets, and it's somehow customary to just say that if there's a different index, it's a different operator. If you find it confusing, you can always ask. Also, this condition, it's only sometimes enforced, as this is some form of non-triviality condition. So what's going on? We just want to look for operators that if we trace them against product density matrices, we get a positive number. By the definition of separable states. If you do convex combination of positive numbers, you still get a positive number. So then it will happen that that this kind of expression for any separable row AB will be positive. Which means that if we then evaluate this to a negative something, the state must be entangled. Okay, so this part is the first part, what holds for separable states, and this part says that it should not hold for at least one entangled state. That's why we call this the non-triviality condition, because without this we can also still say that it's a witness, but it's a trivial witness because it's a witness that doesn't witness anything. It depends how you like to define things. Does anybody know an example of an entanglement witness? So I'm going to claim now that for qubits, this operator is an entanglement witness. What do we need to check?
I mean, first that for all density matrices of this form, that it's greater or equal to 0.
Yeah.
Or I mean, in a tensor product with another such matrix. And then we also need to find a sort of 4x4 matrix, which is also a density matrix, for which the trace together with this operator is less than 0.
Exactly. So the first thing that we need to look at is this expression W. I have tactically changed this sigma to omega because I already am using sigma. And we need to look at what this is. So the first term is going to be just trace over these two things, and that's going to give us 1. The second thing will be minus trace over omega A sigma x times trace over omega B sigma x. And the third term is going to be the same but with z. And what I'm going to do is that I'm going to put this in a bracket. Now this is quite nice expression, because now I can say that, look, this looks like a inner product of two-dimensional vectors. You know, it's like I can say that this thing and this thing is essentially something like components of a vector, and this thing and this thing is something like a components of a vector. And if I have inner product, I can do Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality again, linear algebra, anybody remember? The absolute value of an inner product, or the inner product for the sec itself, must be less than the product of the norms of the vectors.
Front board on the bottom and the back one on the top.
Yes. Oh, sorry?
If you take the front board and put it on the bottom and the back board and put it on the top.
Oh, you mean like this? Ah, yes, and now I can keep writing here.
Yes.
Yeah.
Good, thanks. So applying that there, we get that this trace of W rho A times omega B is less than 1 minus, and here we get norm of R times norm of S, where now the vector R can be defined as this vector that contains trace row A sigma x, trace row A sigma z, and S is the vector that contains trace row omega b sigma x, trace omega b sigma z. But here comes the big trick. This is nothing else than just the block vectors of those two operators if we would input in the middle here the trace row A sigma y and the trace omega b sigma y. Which means that the norm of R must be less than 1 and the norm of S must be less than 1. And of course I got the inequality the other way, because there's a minus, which means it will flip this sign. Which means this will be positive, because this is product of two numbers less than 1. Now we need to show the second point, which is the violation or the non-triviality. And for this space will be enough, because I can just tell you that the state you take is this bell pair, and you are going to use the properties that sigma x tensor sigma x on phi plus is the same as sigma z tensor sigma z on phi plus, and from this you get that trace W with row AB is equal to -1. Because the first term will give you +1, but this term will give you -1, because this will just disappear, and the minus will stay, and this again will disappear, the minus will stay, so +1 -1 -1 is -1. So it is a witness. Now there's going to be a good news and a bad news. The good news is that whenever you have an entangled state, I can prove that the witness exists that would detect this, which is in principle nice, because if you, for example, look at this witness that we have here, this is something like easy to measure, because you just tell the experimentalist that, okay, you're going to run 2 experiments. In the first experiment, Alice and Bob are going to measure the mean value of Pauli x, and in the second run, they're going to measure the mean value of Pauli z. We're going to compute this kind of expression, and if it's negative, then the state must have been entangled. So in this sense, like, witnesses are experimentally friendly to measure, and the good news is that for every entangled state there is going to be a witness. The bad news is that it's hard to find, and there is no witness that would detect all entangled states. So now we'll spend some time proving those 2 statements, and it should go quite fast. So as I claimed, the first proposition that we want to prove is that if row AB is an entangled state, then there exists W, a witness, such that the trace of W against row AB is negative, or in other words, that this is the W that detects the entangled state. Now this proof actually uses some heavy machinery of convex geometry, because what this is based on is the Hahn-Banach separation theorem. And this is rather intuitive result. It's just not, I would say, not so intuitive to prove. But it says that if we have a set like this, which is convex and closed, and we have a point here, then there exists some kind of line that separates those two from them. And we can call this the separating hyperplane. So in our concrete example, this is going to be the set of separable states. And this is going to be the entangled state that we want to detect. Now, if there exists a separating hyperplane, this means that there exists a linear functional f. So this hyperplane is in one-to-one mapping or equivalent to existence of functional f, where a functional is just a linear function. And the way you can imagine f is that it's somehow telling me that how far are you in something like a orthogonal or the perpendicular projection from the hyperplane. And you also have to choose some signs. So this would be the plus side and this would be the minus side here. And for arbitrary point, you just always find the shortest point and then just output that length. That's somehow how we can imagine this functional f. And then what this tells us that if we choose the signs correctly, then we are going to have that this is going to be chosen as the minus side and this is going to be chosen as the plus side. So we'll have that this value, since it's on the minus side here, it's going to be less than 0, and this will be strictly smaller than this, since that's a point somewhere here. This is the sigma A times omega B. Is this at least intuitively clear? Now, there's another thing that we need to prove or know, and that every functional, when evaluated on operator, since the operators, they form the Hilbert-Schmidt-Hilbert space themselves, can be expressed in the form of tracing against another operator. Or in other words, every functional on a matrix can be expressed in this form, and that's roughly because in this form you can get access to every component of the matrix, and then you can build anything out of those. Which means that we just get here this trace f rho AB will be less than 0, and this will be less than trace of f omega sigma A times omega B. And then this is the witness that we are looking for. So now this is our witness right here. Well, here's the bad news. There is no entanglement witness that would detect all states. And the proof is done by contradiction. Done by contradiction that we are going to construct two entangled states. We are going to assume they are both detected by the same witness, and we are going to show that this is not possible. And these two entangled states are going to construct them. We are going to take vectors psi1 and psi2, which are orthogonal and orthonormal vectors, and then we can construct these entangled states, which are, so this is two states, one is defined with plus, the other one is defined with minus, and the one defined with plus is denoted with plus, the one defined with minus is denoted with minus, and you just define them in the usual way as Bell pairs. And now the trick is that if you take this one and you add it to the other one, what you get is that here I'm going to have the 1, 1 and 2, 2 terms with plus, but in the plus I have the 1, 1, so here I will have the 1, 1 and 1, 1 projector and the 2, 2 and 2, 2 projector, but I will also have the cross terms with plus, but in the other one I'll have the cross terms with minus. So they're going to cancel each other. But now this is unnormalized but separable. If you want to normalize it, you would have to divide it by 2. But now there's the thing that if I now assume that, that there exists a witness that's negative on this state and negative on this state, it also must be negative on both of these states, but as somehow contradiction because these are separable and the witness has to be positive there. That's how you get the contradiction. One can again see this as a picture because we can now say that what we just did is that we have the set of separable states here, and we found an entangled state here, an entangled state here, such that if we do the average, so if I would divide this, I would get the average, we get something, so that's roughly here, which is separable. So then if you would have a witness that would be negative here and negative here, by linearity it has to be also negative in the middle, but that's not possible. That's how this proof works. So the only thing to finish this is to check whether this is true, which I guess you can do yourself. So so the witnesses are nice because we in principle know how to measure them, but they're not nice in the sense that there is no universal witness, and finding a good witness is usually could be a lot of work. Of course, there are some standard constructions and some things that are known how to do, but this sometimes works, sometimes does not. That's why we can go now to the second class of entanglement detection tools, and these are positive, but not completely positive. And the completely positive is usually abbreviated CP. And also, I would like to add here linear, but this we are going to usually assume by context that everything is linear maps. So the main idea here is that that we can have a positive map from operators to operators. And the fact that the map is positive just means that phi of A is positive semi-definite for all positive semi-definite A. So who can guess what completely positive means? Yeah.
Strictly greater than 0?
No, but that's a good guess. I'm going to abbreviate it to CP. And what we are now going to do is that we are going to apply the phi to 1/2 of something entangled or something bipartite and require that that's positive semi-definite. So what I'm doing here is that this is mapping Hilbert space H to H, but this A is an operator on H and B such that it is positive semi-definite. And this has to be positive semi-definite. And of course, this should also hold for all Hilbert spaces B that you can put here. But if you want to check this without loss of generality, it's enough to put HB being the same as HA, because somehow there's nothing further that you can do beyond that. So usually the CP maps, you can encounter them in quantum information and quantum thermodynamics, because somehow if you have a time evolution or if you have any operation that you want to apply to a quantum system, it should be completely positive, because in principle, we know that if we are applying our transformation to a density matrix, we are applying it to some 1/2 of entangled system when we're entangled to the environment. And if the transformation would not be completely positive, this would mean that the overall state of system plus environment would not be a state of a quantum theory at all. It wouldn't be described by a value density matrix. That's why completely positive maps, you can encounter them a lot in quantum information. Yes?
Is some square formulation akin to something like a weak topology, or?
No. So the way this is usually formulated is that you introduce something called the Choi-Yamiolkowski isomorphism, which enables you to map a linear map to an operator, and then you know that it's completely positive if the resulting operator is positive semi-definite itself. So that's how this is usually approached. But we are actually going to be interested about maps which are positive but not completely positive. Because if the map is positive, it preserves positivity for a single system, and as we will soon see, it will also preserve positivity for separable things or separable states. But we don't want it to be completely positive, because this will exactly mean that for some entangled state we'll get negative eigenvalues, and this is how we'll witness entanglement. One more note, how to define this. So this identity on B is just the identity map, which gives you out the same vector as you had. And you can always define this in product basis and extend it by linearity. And we know that the operators on H tensor B can be always obtained by linear combinations of operators on A tensor operators on B, which means I can always express this in this kind of product basis and evaluate it there. So the same trick as partial trace. Okay. So now the proposition, or the thing that will always hold, is that if we have if phi is a positive map and rho AB is separable, then phi tensor identity applied to rho AB is going to be positive semi-definite. The proof is extremely straightforward, and as almost all of these proofs go, we just prove it by the definition of separability. So here I plugged in the definition of a separable state, but now since this map is positive, I know that this is positive semi-definite. I know that this is positive semi-definite because it's a density matrix. And this is tensor product of positive semi-definite operators is again positive semi-definite because the eigenvalues are just the products. Sum of positive semi-definite operators is again positive semi-definite, so this works. Now the criterion or the logic that we want to use is that phi should be positive but not CP. And then given a state, so if we have rho AB as a density matrix, what we want to see is that if this thing has negative eigenvalue, then rho AB is entangled. So the important thing is that we want maps which are positive but not completely positive. This is not so straightforward to find. It's not. It's you can, for example, in quantum thermodynamics, they know how to in principle look for time evolutions which are always completely positive, and you get some kind of master equations and Lindbladians, and this can be enumerated. Finding maps that are positive but not completely positive is a bit more work. So what we usually do is that we have several candidates and we just test those. And the first and the most notorious and notable thing to test is the partial transpose. And this is known as PPT criterion because PPT stands for positive partial transpose. And this criterion is so, I would say, well known and so useful that usually this is the first thing anybody would try. Like literally, if you go to people doing research on entanglement and you ask them like, is this state entangled? They would first ask you like, did you check PPT? The idea is that we take our map to be the transpose. So somehow it depends how we want to denote transpose, usually with T, which is just the map that the transpose of matrix is just the matrix where you switch the rows and columns. Now, the important thing to realize here is that this definition depends on the basis in which you write down the matrix. Actually, because the definition of what it means, the star, the Hermitian conjugate, this doesn't depend on the basis because of how it works, but this depends on the basis. So this is not like a single map, it depends on how you write it down, but then usually once you write it down, it will work quite well. So what we need to now prove is that it's a positive map. Did you do this at linear algebra? Or did you show that that if I transpose a matrix, the characteristic polynomial is invariant? Well, then you did it, because if you know that the characteristic polynomial is the same, then the eigenvalues are the same. You can also do a proof, if you want, just by directly checking that this is equal to something like this, where this vector is the same as the vector psi, but with a complex conjugated coordinates. And this will be positive. This will be positive because you know that this is positive if A is positive semi-definite. Should I do it explicitly, or is this hint clear? So the next thing that we need to do is that we need to prove that the transpose is not completely positive, and that's usually easiest to do by example. Can anybody guess the state? So we will again try the obvious state. Or the one that we usually use for everything. So how do we check this? So it should be clear what we want to do. We have this state, we want to write the density matrix, take the partial transpose and show that it has negative eigenvalues. How do we do that? First thing that we can do is we can write the density matrix. How do we now do the transpose? The partial transpose. Yeah.
I guess we just swap in each Canberra indices, more or less.
So I'll denote the partial transpose as T over A. Some people use gamma over A, and this A means over which system you are, transposing, because it sometimes matters. Okay, so tell me what you would like to write.
Well, I would have just kind of swapped. So in the first case, there's no change. In the second term, we swap the two ones with the two zeros, so we have 1, 1, 0, 0. And then we continue like that.
That's the same thing as before.
Yeah.
No, this is the full transpose.
Okay. Right.
So this part and this part is not correct. This part and this part is not correct. It's a linear map, so I can apply it to each term one by one. And we have to remember that this is but a shorthand for this. But I want to apply the transpose to just the first thing, which means that I just want to go with where here on the system A, which means that I just want to apply the transpose here. So the final question is, what does a transpose do to this operator? And you were correct, is that in the sense that if I have this one and I transpose it, I get this one. Because it has just real value, so it's the same as Hermitian conjugate. So what then we do is that if you apply the partial transpose to this thing, you just switch the first two. So you get 1, 0, 0, 1, and here you get 0, 1, 1, 0. Good. So we need to prove this has negative eigenvalues. What's the best way to do that?
Probably not the best way, but I would have calculated the tensor products as Kronecker products, and calculate matrix, and think we get a 2 by 2 block in the middle. We would diagonalize that one.
Yes. I should say that's the best way to do it, but I would say the best way to do it is just like ask a computer to do it for you. So the idea here is that if we have these kind of objects, we can express them as matrices, because instead of tensor product, we can use the Kronecker product to somehow express the tensor product of two 2 by 2 matrices as a 4 by 4 matrix. And the way this is done is that if you have something like ij tensor KL, or at least the way I remember this, you're free to remember the way you like, is that this tells you which block, and this tells you a matrix element. What this means is that we are going to make a 4 by 4 matrix and split it into blocks, and we are going to say that this is the 0, 0 block, but this tells me which block. This is going to be the 0, 1 block, 1, 0 block, and 1, 1 block. And then if I have, then this is going to tell me what matrix I should write in here. Is this clear? This is something that's somehow good to practice a little bit, and make sure that you don't do it the other way around, because it's surprisingly easy to say that this is the block, this is the matrix, and then somehow your code stops working and you get wrong results. Except for sometimes if you do this in simple cases, it doesn't matter. So then if you want to see why your code is wrong and you try a simple example, it will work, but it will not work in the more specific example, and you're going to spend a week trying to figure it out. Anyways, what's going to be the matrix in this case? So we have the 0, 0, 0, 0, which means in this block we are going to write the matrix 0, 0, which means it's just this matrix. This is going to be in the 1, 0 block, which is this one, and we're going to do the 0, 1 matrix there, which is this one. This one is going to be in the 0, 1 block, so this one, and we're going to put the 1, 0 matrix there, which is this one. And this is the 1, 1 matrix in the 1, 1 block, so it's going to be here. Now the important thing happens here. There's two ways to see this. Either we have something like a block diagonal matrix, which is positive sum-definite if and only if all blocks are positive sum-definite, so we just need to look at this part here. Or we can always say that if you have a 0 on a diagonal of a positive sum-definite matrix, then the whole row and the whole column must be zeros, otherwise it's not positive sum-definite. Which is roughly the same logic. In this case, if you want to find the negative eigenvector of this, what you do is that you take a eigenvector which just acts on these two blocks, and you're going to take exactly this one. And why do I know that it's this one? Because this is essentially sigma x Pauli matrix, and this is nothing else than the minus eigenvector of the Pauli x, except for I'm not putting here 0 and 1, but 0, 1 and 1, 0, because this is the 0, 1 and 1, 0 rows of the 4x4 matrix, which shows you that that thing is not positive semi-definite, so the state is entangled. Here's a very nice theorem, and this is something that's very useful to know. And this is that if your dimension over H is equal to 2 and your dimension over B is 2 or 3, then if you take any state, rho AB, then we have that the partial transpose over A of rho AB is positive semi-definite if and only if rho AB is separable. The important thing is that now, in this very specific case, it's if and only if, which means that if you have two qubits or a qubit and a qubit, and you want to see whether a state is entangled, you just need to check one criterion, and it's the one-size-fits-all solution. And in fact, there's a recent result that this is literally the only case when you can have a one-size-fits-all solution. Even if you would change partial transpose to a different thing, this is the only case when you can have like a reasonable characterization of all entangled states. Also, like if you would change the dimension here to 3 or the dimension here to 4, counterexamples were known long before. And somehow the proof here is based on the fact that is based on the Stromer-Voronovich theorem. So which tells you that if you have a map that goes from 2 or 3 dimensional vector space to Hilbert space to 2 dimensional, and if it's positive, then this phi can be written as the sum of a completely positive map and a completely positive map that's somehow done after a transpose. This is again a very specific property that holds only in this case, that if we have a positive map, we can say that it's either completely positive or it's a partial transpose. So this is over, no, this is just a transpose, and then a completely positive map or just some or combination of those two. And this implies that if you have, in this case, a positive but not completely positive map, it's not completely positive only because of this transpose here, which means that the partial transpose is the only thing you need to look at in this kind of scenario. And any entangled state must, if it's detected by any positive but not completely positive map, it's detected by the partial transpose. So now, to conclude the argument, you just need to argue that any entangled state can be detected by positive but not completely positive map. And this can be done because if you would play with this for quite a while, you can realize that from any positive but not completely positive map, you can construct an entanglement witness, or rather if you have the P but not CP map and you have the negative eigenvector, then you can construct an entanglement witness for that state from that. And also the other way around, if you give me an entanglement witness, I can give you some positive but not completely positive map. Somehow that's how you finalize this proof. So there's more hoops. And if you want to study this, the key thing here to realize or to somehow see how to construct a positive but not completely positive map from a witness is to look again at the Choi-Yamiokowski isomorphism or these related results. But this is roughly how the proof goes. All right. Another interesting map that we can do is the reduction map. And this then gives us the reduction criterion. And the idea is now just to define the map like this, which again, I claim is going to be positive, but not completely positive. So the proof is again from the definition. So what we do is that we just put this inside the same vector, and then just plugging in the definition, we get trace A minus psi A psi. And the big trick is just to realize that if I have this psi, I can assume it's a normalized vector, so it has norm 1. And if it's a norm 1 vector, I can find a basis such that this is the first element of the basis. But that just means that this trace can be written as psi A psi plus a sum over some other vectors phi A phi. This cancels with that, and you just get the sum here, which is positive because all of these terms are positive. There's a reason why people don't use this too much, is because the reduction map is can be reduced to partial transpose. You can somehow show that this reduction map can be in a way similar to this, decomposed into something concerning partial transpose, which somehow shows you that the reduction criterion coming from the reduction map is strictly weaker than the BPT criterion. Why this is still interesting is that there is a connection to distillability of a state and violation of the reduction criterion. So somehow, because it's weaker, you can prove that if state is detected by the reduction map, then it's distillable, which is not true for partial transpose. And in fact, the big open question I mentioned on the last lecture is whether there exist states which are bound entangled but somehow violate the PPT criterion or are detected by the PPT criterion. Moreover, the nice thing here is that using the reduction map, one can prove a very nice proposition. So we can prove a nice result. So do you remember that we had this monogamy of entanglement result that told us that if a partial trace of a quantum state is pure, then the state is a product state? Like one lecture ago. And from this you can somehow deduce that if I have a pure product state, so it's a projector tensor projector, the partial traces are again pure states. If I have an entangled state, just like this one, the partial trace is a complete mixture, so it's 1/2 of identity. So it's a very mixed state. And from this one can get the idea that maybe if the marginals are more mixed than the whole state, then the state is going to be entangled. And this proposition actually just expresses this in more exact terms. Because it just says that if rho AB is separable, then the purity of the marginal is bigger than the purity of everything. So this state exactly violates this, because this is a pure state, so this would be 1, but the marginal of this, if you would compute it, would be a mixture which has a purity of 1/2, 1 over dimension. So exactly this wouldn't hold. And the proof of this is rather, I would say, cute exercise, because we proved this by using reduction map and then sum. Because from the reduction map, we know that if this is separable, we must have that identity on A times the trace A of rho A B is bigger than rho A B. So what I did is that I just took this map and applied it to the B system as this, and then assumed that it's positive semi-definite. I know that's true for separable states, so I can throw this on the other side of the inequality. You get this. And now what you can do is that if you have a inequality between operators and you trace that against the positive operator, then you still get the same inequality. So what we are going to do is that all of this side we're going to put into a trace and multiply it by rho AB and still get the same inequality. So what this means is that take this part, put it here, take this part, put it here, you're going to get the same inequality because this is positive semi-definite and this is an inequality. So what we get here is, yes. But now by using the definition of partial trace, we get here partial trace over A twice. And if you remember, this is exactly the definition of this purity. This is exactly the definition of this purity, which concludes the proof. The nice thing about this criterion is that it's very easy to check. Moreover, it's very easy to check even for infinitely dimensional systems, because all you need to know is how to perform partial trace, which you usually know, and how to square stuff, which you usually know. Because if I would ask you, for example, about entanglement of two harmonic oscillators described by infinite dimensional Hilbert spaces, then it's like performing the transpose takes some kind of conscious effort. But this thing is very easy to check. And moreover, you can somehow check or persuade yourself that if you have a pure state, then this is sufficient. And many times you can somehow say that, well, in a good enough conditions, I have a pure state, so, or close to a pure state, so this will still work. But it's also a very weak criterion. It's if you're going to be doing some very heavy stuff with very noisy systems, it's not going to help you, but it's somehow good to keep it in mind for the complicated situations. Another criterion is called the range criterion, and this says that if my state is separable, then range of rho AB, so rho AB is an operator, and as an operator it has a range, is spanned by product vectors. The proof is, well, just take the range of that in computational basis and you'll have it spanned by product vectors, because if this is, let's say if it would be product, then it would be of this form, spanned by product basis. If you do the convex combinations, you're just doing linear combinations of those vectors. Now, this criterion is rather strange because it's very hard to check. Like, you can see that this result is true. This would be a way to detect entangled states, but it's somehow not obvious. Like, for partial transpose, I can give you immediately an example where we see something is going on. For reduction criterion, you can try the same thing, essentially also based on this. Here, this is not so straightforward to do, but still this criterion is very important because this criterion can be used to detect states which are not detected by the partial transpose. And this was something fancy to do some years ago, that people were saying that, oh, we have a lot of states that are PPT, so they have positive partial transpose, they're not detected by this criterion, and they realized that, well, but if we do this criterion, then at least in some theoretical cases, we can still detect it. But sadly, this criterion is not practically very good, because if you have your state and you start adding something like a noise to the state, so you start assuming that because the state is transmitted through optical fibers, it's going to have a little bit of noise, a little bit of this and that. Sometimes the state doesn't arrive okay. You'll soon realize that the range of the state is going to be full, and so then you're going to have then it's not going to work anymore. Finally, one criterion that's that you should know, or that's also often used, and you can find it referenced often in results because, again, it can detect states which are not detected by PPT, is the realignment or CCNR criterion. And the CCNR stands for computable cross norm. Criterion. And the thing I like about this criterion is that it actually, I find the idea mathematically nice of what's going to happen. Because when we have a density matrix, it belongs to the set of density matrices on the product of Hilbert spaces. And this is nothing else but the subset of all operators. And moreover, since we can get any operator as a linear combination of products of operators, this can be seen as the product of two vector spaces. Moreover, both of these things are Hilbert spaces themselves. And I don't mean the HA and HB, I mean the whole thing here, the operators on a Hilbert space in a finite dimensional case, they again form a Hilbert space. So it's a Hilbert space of operators or the Hilbert-Schmidt space. And the way you define an inner product of two operators is by putting them in the trace and doing the star of the first one. You had this on algebra or quantum theory or?
No, we just looked that up.
When?
10 minutes ago.
Why?
Earlier when it was about the Hahn-Banach separation theorem, where we also had the functional.
Ah, okay. Yeah, that's somehow related to.
Kind of use it.
Yeah, it's kind of related to this. It's actually yeah. But since this is a Hilbert space and this is a Hilbert space, this is the tensor product of Hilbert spaces. Now, if you go back to your notes from the last lecture, we said that if I have a vector, say psi, which belongs to a product of two Hilbert spaces, then I can write psi in the Schmidt decomposition. And now I can do the same thing, except for now the Hilbert spaces are the Hilbert spaces of operators, but it still holds. And I would somehow say that this is like an important thing in mathematics, because you just write down what you have, then you realize that this is actually also something else, and then I can use the results for something else. Yes?
I think it might be something alike to, well, something about the duals. I'm not sure, but maybe it looked a little bit familiar. This approach of the separation of the operators.
Well, yeah, it's this thing that we had last time, but now you, instead of using vectors, you use operators.
Yes.
So and now the result is that rho AB is separable than the sum of the Schmidt coefficients of itself when seen as element of the tensor product of two Hilbert spaces is less or equal than 1. Now, the nice thing about this is that if you remember last time I told you that you can easily obtain the Schmidt coefficients from the vector itself, which means that suddenly after the range criterion we're again with criteria that we can actually easily compute. And to do this, what you do first of all is that we can say that if I have a product thing, if I have a product state, then this is already written in its own Schmidt decomposition with 1 here. And so then we get that the sum over k lambda k is just something like lambda 1, which is equal to 1. If we start doing the convex combinations, this is going to just decrease. And now the argument is a little bit convoluted. are a little bit not so straightforward, because what we now need to realize is that in some sense, this sum of the coefficients can be seen as some kind of norm of this operator, but this is the Schmidt norm or something. Or in general, if you have a vector and you sum the Schmidt coefficients, this is a norm of the vector, but it's not the normal norm of the vector, it's a different norm of the vector, because you can have more than one norm. How to see this is that you can realize that these coefficients lambda k, they are eigenvalues of C star, where now what we can do is that we can express this as sum over ij, and here we have the Cij, and here we have some two arbitrary bases. Now, these are orthonormal bases of operators, and orthonormal in the sense of the inner product of operators, okay? But if I would somehow write this here, and this here, and this here, we would have the same thing that we had on the last lecture. Just it's still a Hilbert space, just the symbols change. And since these are of the square root of this, you can realize that some of the eigenvalues of a square root of a matrix is a norm of C, and thus we get that the sum of the k lambda k, this is equal to some norm of C, and this norm is called the trace norm, or well, I can maybe write it like this. It's the trace of this thing, and this can be seen as a norm on C. And this is either the trace norm, or nuclear norm, or Kifan N norm, or the Schatten 1 norm. As you can see, many people thought about this idea. But since it's a norm on C, it must be a norm on row AB, because this row AB is in one-to-one correspondence in C. If you give me row, I can give you C by using this decomposition. If you give me C, I can give you back row by summing this. Which means that this sum is a norm, is some kind of norm of the row. It's not an operator norm, it's not a trace norm of this, it's some kind of norm of this. It's neither of the ones that you would usually think of, but it is still a norm. Which means that then when I express this as a convex combination of these objects, I can just use triangle inequality to get what I want.